Hello, this is Sumnik. I will be solving educational routing codiforces and trying to explain what I'm doing. Oh my god, it's FizzBuzz. So we construct a FizzBuzz string without numbers, just F and B. We are given a string of length at most 10, and we we need to check if the string is a substring of FizzBuzz string. But FizzBuzz string is periodic. With what period? With period 8, I think. Like this should be the period, right? Like when we traverse first 15 numbers, and then it will be repeating modulo 15. So we will do the same stuff. So our infinite string has period 8. That means that if it has an occurrence of some string and the left border of this occurrence is at position 8 or more, we can shift this occurrence by 8 to the left. So the left border of the occurrence can be from 0 to 7. And since our strings will be up to length 10, we just need like first 18 or something symbols, and then we can check all the substrings just in this stupid way. So we first construct string s, and something should be enough. So I should have at least 20 symbols, and then for each query so I read the string and just check if it is a subsegment. There should be like inbuilt function to do that, but I don't know how it is called. So I will just check all the starting positions, which, as I said earlier, I can check only from 0 to 8. That's fine. So I'm taking substring starting from position I with length equal to length of p, and if it is equal, then answer is true. Oh, first it's length. I should read it for some reason. Problem B is again about strings. How come educational rounds have so much strings? Because all the problems about strings are boring and can't be put in actual rounds. That must be it. Template T is a string of lowercase letters and asterisks. Template is asterisk minor if the number of asterisks is less than or equal to the number of letters. Okay, so at most half of the characters can be asterisks. String is said to be matching a template if you can replace each asterisk with a string, not one character but a string, and possibly an empty string, so that it becomes S. And we are asked to find an asterisk minor template such that both A and B match it, or say that it's impossible. And we don't have to minimize anything like length, number of asterisks. Whatever is fine. Okay, so empty template is bad. Thus, we should have at least one character, letter, I mean. So, well, that means that this letter should appear in both strings. So, both strings should have some equal letters. Then, like, asterisk, this letter asterisk would match both of them, but this again has more asterisks than letters. So if we only have one asterisk, then either first symbols should coincide or last symbols should coincide. If none of that is true, then we must start and end with an asterisk. Obviously we don't have two asterisks in a row, but if we start and end with an asterisk, if we don't have two letters in a row, there will be strictly more asterisks than letters. So either first letters match, then we can just put this letter asterisk, or last letters match, in which case we can put asterisk this letter, or we should have two consecutive letters in the template. That means that in our two strings, those two letters should be also consecutive and in some position. But then if that holds, then asterisk those two letters asterisk works. So we should check if first letters are the same, last letters are the same, or there are two positions in which two letters are the same. And since the limitations are small, we can just try pairs of positions, right? Like 10 to the 4th times 50 times 50 should be okay. It would be possible to do it faster, right? Like it's solvable in linear time. We can just mark all the pairs of consecutive symbols in the first string, and then traverse the second one, and if we find a pair of consecutive characters that was present in A, it will be good. So that's linear. Or like if alphabet is big, then we should use something like set, or well, with hash set with an ordered set. Still linear, but like it's bad constant, or like n log n. But the limitations are small, so we can just check stupidly, and if the limitations allow you, like, stupid implementation is better because it is less likely that you will have a mistake in it. That doesn't always mean that slower solution is easier to implement. Like it can be the case that the solution is slower and harder to implement, and can have more potential mistakes. Should I like print yes first? So if the first symbols are the same, then we print this symbol and then asterisk. If last symbols are the same, then we first print asterisk, then this symbol. Now we iterate over all but last position in the first string and in the second string, and if this pair of symbols are the same in both strings, then we print asterisk, then two symbols, then asterisk. And otherwise it's impossible. Problem C. Set of positive integers is beautiful if for every two integers from the set, one of them divides the other. So like smaller divides bigger, obviously. So we are given some segment of integers. Consider all beautiful sets that are subset from the segment. We have to print two numbers, the maximum possible size and the number of such sets. Okay, so how does a set the sets that satisfy this property. Look, if we sort the numbers, well, this property should hold for consecutive numbers. So, like for each pair of consecutive numbers, the left one divides the right one. I think there was like a similar thing recently. So we have first number, then we multiply it by something to get second number, then we multiply it by something to get third number, and so on. But that would mean that, well, if we have this form, then the property holds, because for every two numbers, like their quotient is just the product of all the numbers we multiplied on this segment. So the set is defined by starting number, and by which we multiply each time. We should multiply by at least 2. And if we start with minimum number, which is L, and multiply by 2 each time, we will have maximum numbers. How can we get other sets of the same size with this property? Well, we should change those multiplications by 2 with something else, and or change the first element. So if we change the first element, and well, let's say that we will fix like this pattern of by which we multiply, and then for each such pattern we will calculate how many starting positions are good. So what is important for us, like from the starting point, when we multiply by all of them, we will reach at the last number, and it should be at most r. And we know that, well, our answer, like how many times we multiply by 2, is like what is the largest power of 2, such that L times this power of 2 is at most R. So if we increase this number by which we multiply by a lot, then even if we start with L, it will be bad. By how much? Well, okay, let's write it. It's not that easy. So we start with some number, and we have like this C coefficients by which we multiply. So like I is equal to A0 multiplied by all these coefficients up to this one. So we know that A0 should be at least L, AK should be at most R. So for fixed set of CIs, so AK is just A0 multiplied by this product. We know K because, well, we know that like the greedy way is to just place 2 everywhere, and we can check like how many times we can do that. So what are the inequalities that A0 should satisfy? Well, we know that it should be at least L, but also AK should be at most R. So A0 multiplied by this product should be most R. We can divide R by this product, and thus we will get that the limitations on A0 are as follows. So it should be between L and R divided by product of all Ci. We can round this down, and then like the number of corresponding A0s is just difference between this and this plus 1. Okay, but if this is smaller than L, then it's already bad. So we are interested to understand when that happens. And we know that if we would add another 2, it would be bad. So like we know that R divided by 2 to the power of k is okay, but if we increase this power by 1, then it will be bad. So how can we change? How can we choose number C? Well, I state that either we just choose all 2's, or we can change one of those 2's to 3, and that's it. Why is that? Well, if we change one of the 2's to 4 or something bigger, it is the same as multiplying by like this number divided by 2, but that's at least 2, so we will already get something bad. And if we will have 2 3's, then we multiply it by 3 over 2 times, but that's 9 divided by 4, which is again greater than 2, so that's also bad. So either all 2's or change one of the 2's to 3. It doesn't matter which one we will change, like then this value will stay the same, but we need to multiply it by k, because we can choose which of the 2's will change to 3, and that will change our numbers. Okay, so the solution works like that. We find k, which is maximum such numbers such that L times 2 to the power of k is less than or equal to R. And then we calculate the difference of this and this plus 1 for like this set of C's that all 2's, so their product is 2 to the power of k, or we can change one of those 2's to 3, and we should do that only if k is at least 1. It doesn't really matter, because we will multiply it by k, which is 0 when k is 0. But still, like you should think about it. If we will somehow divide by 0, that's not good. For example, you can say, okay, let's take 2 to the power of k, solve for it, and then how to get like change 2 to 3. Okay, let's divide by 2 and then multiply by 3. But if k was 0, then this will be 1. We will divide by 2, probably rounding down. We probably do this in integers. You will get 0, then multiply by 3, 3 still 0, and then you will divide R by 0, and this will be not great. So multiplication by 2 to the power of k is just shift to the left by k. So I'm like with this file I will find the first k that is bad, so I have to do k minus minus here. Since the second number can be very large, printed modulo, no, it cannot. Yeah, our k is like log, so it's at most 20, and then we like the difference of two numbers that are at most 10 to the 6. Yeah. Like I think that the actual upper bound on the answer is something like 500,000. But yeah, it's not a stupid decision here. Like they just want to hide the fact that the number is actually small. To divide r by 2 to the power of k and round down, again we can just shift right this time. So now I want to divide by 2 to the power of k minus 1 multiplied by 3. First I will shift right by k minus 1, then divide by 3. And yeah, this number can still be so big that like r divided by it is smaller than L. So I should add to answer only if like there is something to add. Otherwise we will add negative numbers and that will ruin the answer. Okay, multiply by k. Said it, but forget to do. All right, problem D. An array k and x performs the following operation exactly once. Add x to elements on exactly k distinct positions and subtract x from all the others. Okay. Let fa be the maximum possible sum of a subarray. Empty subarray should be considered. So I want to maximize maximum subarray sum after the operation. In k is at most 20. It's a nice problem. So instead of doing this, we will first subtract x from all the elements, and then for k chosen elements we will add 2x. That's the same, but now we're changing only k elements. And now we can say the following. Oh no, it's actually very simple. Or is it? Oh, x can be negative. All right. Well, the first solution I thought about still should work. But that might be a bit overkill. Okay, so there is like greedy solution and dynamic programming solution. So let's start with like I will explain the greedy one, then I will explain the dynamic programming one. I will probably implement dynamic programming one because it's less prone to mistakes, I think. Okay, so greedy solution. So we have an array. We can flip the order in which we do the operations. So operations to choose where we will add to x and which segment to choose after that. We can first choose the segment, but then like if x is positive or like non-negative, then we would like to increase elements inside our chosen segment and don't care about the outside world. We can always fit operations, like the issue is like is choosing where to put them. But if x is negative, then it's not that good. Like we don't want those operations, so we would like to choose elements outside. But if we have to choose more, like the number of elements outside is not enough, we don't have k elements outside, then we will have to choose something inside and increase it there. And here we can use that like our change to the array is adding something, and the function we are calculating is also sum on segment. So it doesn't matter to which positions inside the segment we add 2x, the result will be the same. We only care about like how many times we can add. So here we will add like minimum of length of the segment and k. Like we have k additions, but we cannot use more elements inside the segment that there are. And here it's like maximum of 0 and it should be like k minus n minus length, right? Like n minus length is the number of elements outside, so this number of decreases in this case we can spend outside the chosen segment, and everything else should go inside the segment. Okay, so look, we will separately solve positive x and negative x. If x is positive, we want to choose a segment that maximizes sum on this segment plus this times 2x. If length is small, so that length is smaller than k, then we can just try all such segments. There are only n times k of them, and calculate the function for all of them. And if we guarantee that length is at least k, then we know that we will just add k times 2x. So we just want to find the segment with the largest sum among them. That is similar to like how you just usually find segment with maximum sum in array, except like the algorithm works as follows: like you go left to right and you maintain the smallest prefix sum you have seen so far, and then like take current prefix sum minus the smallest. So like the sum on segment is prefix sum in the right point minus prefix sum in the left point. So we want to maximize that. That means that for fixed right point, we want to minimize prefix sum in the left point among available, which are like to the left of R. So the ones that we have seen. Now it's kind of the same, but the available is the ones we have seen at least k before. But that just means that those two pointers we are moving are not at the same point. We should like move those two pointers with distance k and maintain minimum prefix sum we have seen like up to this pointer, but take like update the answer in using this as the right border. So that part is linear, just O of n, and trying all the short segments is of n times k. You can actually do it in O of n. Look, and log n is even simple enough. We can just say that okay, we will increase all the elements by 2 times x. Let's just increase all the elements by 2 times x. Now we want to find the segment with largest sum with length at most k. Again, we can do kind of the same thing, but now we are interested in minimum of prefix sums on this segment. So we can use some data structures to do that, or like do scanline that will maintain current options in set. All of that is n log n. But you can actually do scanline that maintains options in Q with minimum. This data structure exists. So that's O of n. Okay, now the second part. So now like either our segment is very long, so like it covers almost everything, and again we can just try all such segments. There are even like of k square of them, even not nk k squared, because left border should be among first k and right border should be among last k. In that case, we will have to like subtract something and update the answer. Otherwise, we will not subtract anything. Now we just want maximum sum of a subsegment that has length at most like n minus k. so such that this thing is not positive. And again, we can use this thing that I mentioned to do it in of n, but also we can do it stupidly using that case small. We can say that okay, if right border is not in the last k, then we don't care. We know that length will be small, so just on this array, which is everything but k last elements, we just solve the usual, like find segment with maximum sum, or right border is among those last k options, but then we can just try all such segments. Yeah, so that's greedy solution, like naively implemented, that's of nk, but we can do of n, which is actually nice. Like that's probably not what authors meant, because why k small? Okay, now the DP solution. So the idea for the DP solution is like we will do scanline kind of. And we have like some choices to make. Choices include like which elements to do this plus 2x, which can be actually negative, where to start the segment, and where to end it. Okay, let's just put all of that in DP state. Like from this, we only care, like we have to choose exactly k elements in the end. So we only care about like how many times we have already done that. Okay, so we will have DP prefix. Operations, either already done or like how many we have left, and flag with 3 states before we start the segment, inside the segment, and after. So this is n, this is k, this is just 3, and when we do the transition, we have to make all the choices that we can make. Like when we traverse a place between 2 elements, we choose like whether we want to start the segment or end the segment, and whether we can do the separation depends on the state. Like this flag can only move further in time. And when we traverse the element, we choose whether we do this plus 2x or not. And if we are inside the segment, like in the DP we store maximum sum, and if we are inside the segment, we should increase the DP by the value of that element after we like either applied or didn't apply the operation. So the number of transitions from each state is constant, so this works in of nk. And well, this is a very powerful technique actually, Like for example, it solves the problem like well, do the same thing, but instead of increasing k positions, you can swap k pairs of elements. So if you fix the segment, you want to like increase the contents by swapping something from outside and something from the inside. Obviously, you should choose like the biggest elements outside and the smallest elements inside. But without like trying all the segments, it's not clear how to do that. But with this DP, like you can make these choices like as you go. So you will have so it will be nk squared because you need to like choose k elements outside and k elements inside. And so when you choose an element outside, you add it to the score even though you are not inside the segment. And when you choose element inside, you don't add it to the score even though you are inside the segment because you will swap them. And like in the end, you should choose k elements outside and k elements inside, and this DP will find the optimal way to do that, which is nice. So yeah, this is a nice technique. Let's do that. Kind of want to have this. That might be a bit too much memory. It's like 12 million longs. That's 100 megabytes. It's fine. So the first thing I said is that we will subtract x from every element and then just multiply x by 2. Now we have to choose k, exactly k elements to which we add x. Yeah, if I actually had issues with memory, we can only store 2 layers of DP. So we don't actually need NK memory, but since we can afford it, why not? Okay, so I want to iterate over borders and elements. So border element, border element, border element, border in the end. So I will iterate up to n here, and first I should do the transitions that correspond to ice border, and that is done by saying that we can move to the next stage now if we want. Now I don't want to make transition with nth element which doesn't exist. Here I want to make a decision whether I want to choose this element. So but also if I do choose it, then I should have chosen less than k elements before, so j plus t is at most k. That's actually like, that will be the new parameter j, and it should be up to k. And if we're inside the segment, which is which means that flag is 1, then we should increase this value, like add to this value, maybe it's not increasing, current element plus, if t is 1, if we change this element, then also x, that is x multiplied by t. And in the end, we should choose k, like we should be in the end, choose k elements and close the segment. That's why we need like this part when I is n, because we should be able to close the segment, or like I could do it here, like print maximum of 0, 1, 2, but like that's a more correct way to do that, kind of. And it doesn't work. Yeah, I should do this here, because like I'm changing the value. That is correct. Problem E. Have a tree. Select vertex R, probably stands for root, and for each v, dv is the distance and we choose a color probably for the vertex. Nice coloring satisfies two conditions. For every pair of vertices of the same color, there exists a path that only visits vertices of the same color. So like we should split in the like connected components. We cut some edges and every component will have their color. And for each pair of vertices of the same color, distances are not equal. Okay, so this means that if we have colored some vertex, like let's root the tree in R, obviously. If we have colored some vertex, we cannot color two or more of children of this vertex into the same color. That means that each color should be like some vertical path. Okay, we can choose the amount of colors. For each used color counts the number of vertices of this color. The cost is the minimum of these numbers, and we want to maximize the cost. So I want to maximize the minimum binary search and answer. So now for each color we use, we want to color at least that many vertices in this color. So we want to split our tree into vertical paths, and each vertical path should have at least that many vertices. And we can choose the root. Okay. This looks like some 3DP, but we need to calculate it for each root, so we'll have to push it down too. So yeah, we have fix k in binary search. Now we want to check that we can split into vertical paths of size at least k. So let's root the tree somewhere. We have I want to calculate some kind of DP in subtrees. So let's look at the vertical path that contains this vertex. It can go up somehow and it can go down. So there will be vertex in which we go down and some other sons. In each of the other sons we should just split everything into vertical paths of size at least k, and so we will store whether it is possible. Okay, what's for this sum? For this sum, we will kind of want to start DP for this vertical path that goes to root, and maybe we'll continue further, and everything else is split into vertical path of size k, and it should be clear that we want this path to be as long as possible. The longest one, considering that everything else should be split, is good. We have more chances that it will reach the needed size. And actually that just means that whether we can split this subtree into vertical paths, that just means check if this dp is at least k. This vertical path, maximum one that end in root, is okay. So how do we recalculate this dp in this vertex? We calculate this dp in all the sons. We should choose one of them. All other should be at least k. So if we have two sons, at least two sons, which have dp at most strictly less than k, then it's bad, because for one of them we cannot increase this path. If we have one such path, then we have to choose this one, and therefore our dp is this dp value plus 1, because we added new vertex. Otherwise we can choose any one. We will choose the largest one because we want maximum. Okay, so we have calculated this for one root. Now we want to try and push the values down. So here's a vertex with some path to root. It has some sons. Here are some children. So imagine this vertex is a root now. So for this subtrees, the definition of vertical path is the same. Yeah, so yeah, we can just check if all of them can be split fully, then okay, we can use this vertex for this vertical path kind of. Otherwise it's similar to just recalculating dp here. So what's from the highest part? From there we should kind of say, okay, what was the dp value if we assume that this edge is going up, and everything that is up is that subtree, and it seems that we should be able to calculate that just like we did here. Calculate it here. So now that dp value from here, we know the values in subtrees. So if at least two of them of the lower one is if at least two are strictly less than k, it's bad. If one of them is less than k, if it is less than k minus 1, it is also bad, because this is the root and we can only add 1. If it is k minus 1, then I mean, we just consider that up is another sum and recalculate dp. So that's fine. The problem is like now I want to like continue doing DFS, so I want to go down here, for example, and I want to recalculate, understand what is the value of up that I should have here. And it looks like kind of the same thing, except we should not consider this vertex, like this sub-tree as the one that was down from here. So we had like what we got from our parent and all the other guys, and what we needed to calculate dp were like two minimums and maximum of dp values. Well, okay, we can calculate two minimums and maximum on every prefix, on every suffix, and then for this fixed value just like not consider it and make the transition. Oh, like we can calculate three minimums and two maximums, and again not consider this one, so calculate what will be the two minimums and the maximum if we do not consider this sum. Yeah, that works. So all of that is done in linear time, and in the beginning we have binary search, so it's nlog n. Binary search. One is surely good and plus one is surely bad. So first we should calculate dp up, considering that we rooted 0, and then we should run another DFS, probably not like this though. Like for the root we cannot say that something comes from up because we don't have anything there, so we need to be careful there. But let's think about it a bit later. So I need two minimums and the maximum. Well, okay, here I don't care, I can just calculate everything and sort them. I mean, that ruins the complexity, but who cares? If we don't have any children, then our DP is 1. If at least one of our children says that their DP is -1, so it's impossible, then our DP is also -1. If all of if we have one son, then our DP is their DP plus 1. If there are two elements that are strictly less than k, then our DP is -1. If the smallest element is less than k, then our DP is this one plus 1, otherwise we should take the biggest one plus 1. That's it. Now here I should also pass the DP value from up. So yeah, there are a lot of ifs. Probably don't want to write all of that again and like with more ifs to remove one of the children. So I probably want function to kind of recalculate So like recalculate dp will take a vector of like interesting children that are like among minimums or maximums, and actually like the elements are pairs, and like the second element of the pair says which children, which child it is, and we can also like ignore one of the children. So if we should ignore these children, then ignore it. Also, like I will probably like separately calculate minimums and maximums, but if I have small number of children, they can repeat themselves. So I should kind of unique this vector. Okay, so now in this vector we have values from children that are sorted, and only the ones that we should not ignore and like without repetitions. And from here, like I should do exactly that. Except that I should return those values. So here I just want to take all of them and just say dp of v is recalculate dp from a. Alright, so now here for vertex 0 I want to get all interesting options from children of this vertex, and then for each child run the dp, like run the DFS. Okay. Let's just write a function that will, like, from vertex find all the interesting children. So we should be careful to only traverse children. So we need to give this function a parent of this vertex. And here I should run DFS from vertex u with parent 0 and value from up should be like recalculate dp of options that I got but with this sun band. So if I got -1 from up, I will not be able to do anything with that, so just return. VM parent. I should also push back up there without the possibility of it being banned, so like something impossible there. So like yeah, here I should say -1. So yeah, if I don't want to ban anything, I put -1 here, so -2, it can be banned. Right. And I should consider this vertex to be the root. That just means don't ban anything. Like if recalculate dp a-1 is at least k, then it's good. Like this vertex is a good root. Yeah, that looks reasonable, and I need to write get options. I think I probably don't get options here. So get options, the function that takes vertex and parent, and takes dp from all the children. And only leaves like 3 minimums and 2 maximums, something like that. There should be some arrays, right? I have no idea how it works, but something like that. I don't know whether this actually works. It is not checked on the samples, obviously, because this never happens on samples. But who cares? Let's just submit. this actually shouldn't happen. Well, let's Google how vector arrays works. First, last. That sounds right. That's what I want. I should sort the vectors off. Come on. Okay. Instead of sorting, I can call nth element 2 times when to put the right element. Now it is n log n. Yeah, this one could have broken this one, so plus 3 here. It has intended complexity now. certainly has the right complexity now. So, okay, let's just do some constant optimizations. I don't have to call get options twice. Like, get options just takes children and puts them and leaves only like 3 minimums and 2 maximums of them. So I can call it once here and remember the result. So like this is get options from bar and right. I don't need to sort B, and actually, since I implemented it like this, I don't need this. And yeah, instead of sorting B, like I can just get it sorted. Let's say that if that's too much, I will remove things that I don't need and sort A here. So now it's sorted here. Sort it here again. I don't need to go further if I already have ants. And so now here I give sorted A. So I didn't sort. I can not change it at all. Cannot make new vector. Instead, I will calculate size and center small. Center small is how many of them are smaller than k, and size is how many of them exist. So I can check this, I can check this, I can check this, I can check this, and this, everything. So if second is plan continue, otherwise says plus plus, and if first is less than k, small plus plus. So if I don't have any children than one. If I have -1 children, also very bad. So this if is this one, this is this one, and this is also this one. Now this and this are the same kind of, so if something small is 1, that means this one, so I should return the smallest element +1, but the element on position 0 can be bent. And here I should return max +1, but again the last one can be bent. Course, because it's parented. Well, this should be somewhat faster. Assuming it works. Okay, let's read problem F. Okay, so this is problem based on this joke that we can just stroke out 9s, get 1/5, and it's correct equation. So a triple of positive integers a, b, n is strange if this is true where this and this are concatenations. We want to calculate the number of strange triples with bounds on numbers. And a and b up to 10 to the 5th, and n is 10 to the 9th. Unclear. I got past test 18. Non-asymptotic optimizations for the win. I don't even know what to say here. I think that that's intended solution. Just not written like stupid umnik, I guess. Okay, let's try to solve it, and then we'll see if I can implement it. well, we should probably brute force lengths of all the numbers, or at least like numbers n and b, because otherwise it's not clear what to do at all. Concatenation is not a great operation. So let's say that length of A is LA, length of B is LB, and length of N is Ln. Then this says that A times 10 to the power Ln plus N divided by N times 10 to the power length B plus B is equal to A divided by B. Let's multiply it like that. So AB 10 to the N plus BN is equal to AN 10 B plus AB. Oh, it's minus here. I thought it will be just like concatenation. What now? Okay, we can look at this equation modulo A. Then this is 0, this is B times N, this is 0, this is 0. So B times N is 0 modulo A. And well, this should be 0 modulo B. N times 10 to the power of B is 0 modulo B. So A and B are relatively small. What if I fix A? Then we have like bn plus b times a times 10 to the power of ln minus b times a minus n times a times 10 to the power lb is 0. So it's like bn plus b multiplied by something minus n multiplied by something is 0. If I look at b minus q times n plus p, this will be b times n plus b times p minus n times q minus p times q. So I'm doing minus p times q plus p times q. So this is equal to minus pq. And all of those things are integer. Now what is the order of all of that? Can I like factorize this number? So p is a times 10 to the power of ln minus 1, and q is a times 10 to the power of lb. The product is a squared times 10 to the power of lb times 10 to the power of ln minus 1. So I just need to factorize a. This I know how to factorize, and this I can factorize like just for all values of ln separately. And then I can try always to split this into two factors. I don't really like that this is an insanely big number. It doesn't even fit in long, right? Like this has length 5, 9, 5 and 5, so it has length like 24 digits. But that's actually like q minus b n plus p. And like 10 to the power of length b is big, so like I kind of know like this number from which segment it is, and this number. Again, like 10 to the power of length n is big. if A is rather B, this probably means that like B and N like, should be roughly equal to like, B divided by N should be roughly equal to Q divided by P. Not sure if that helps at all. No idea how to solve that. Guess I'm not the only one. No, like people are solving this without time limits. Good for them. I'm not sure how to do that. Interesting round. Thanks for watching. Bye.